Hello, this video will describe our EENG 307 final project on self-driving cars.
Hello, I'm Cameron Kramer, and I will be talking about the problem set. So every year, around 1.25 million people die in motor vehicle accidents. And so, by making cars self-driving and removing the ability for humans to make error, we could potentially make driving safer. And so a control engineer would be responsible for designing the control systems of the vehicle. And so our team focused on the speed control portion of a self-driving car. And so we chose several metrics to design our system, including settling time, overshoot, and zero steady state error. Moving on to modeling, we derived this mass damper function with the mass of the car, the damper for the wind resistance of the vehicle, and a force for the engine. From this mass damping force diagram, we were able to derive this transfer function, which represented our open loop gain. And then to model this and to see what our preliminary system design would look like, we put the transfer function into Simulink, and from that we got that diagram. And then our preliminary variables were a mass of 1,500 kilograms and an air resistance of 8.7 Newton seconds per meter.
Hi, my name is Ian Welch, and I'll be talking about the analysis portion of our project. The open loop plant is stable because it is first order, and there's only one pole located in the left half plane. The pole in the left half plane is located at negative 0.0058. The system is expected to undergo disturbance because of the slope that the car will be driving on. As you can see from the diagram, when a 2,000 Newton force is applied to our system, you can see that is very slow. We have a rise time of about 375 seconds. So in order to correct this, we use a controller which will help speed up the system and also create a zero steady state error.
My name is Matthew Sieler, and I worked on the design portion of this project. And so for the design, we modeled our closed loop system in Simulink. We have our velocity N represented as a step input that goes to the velocity the user set, which will lead to a controller that I'll talk about in a second, which will lead to our plant system dynamics, which will result in a velocity out. We need to account for disturbance as the road will be inclined and declined. We represent disturbance as a unit step input, which will be based on the degree of inclination on the road. So for our specifications, we wanted a settling time of less than or equal to 8 seconds. We figured for a car going from 0 miles to 60 miles per hour, 8 seconds is reasonable for an average sedan. And additionally for overshoot, we want that to be less than 7% because we do not want the car to exceed the speed limit too much. And lastly, we want zero steady state error, so when the car stabilizes, it is at the velocity that the user set. So we chose a PI controller to obtain zero steady state error for unit step disturbances. We needed the integrator to obtain the zero steady state, and we added a proportional controller to make the system faster to reach our settling time of less than or equal to 8 seconds. So our controller is CS equals KI over S plus KP. When we plug that into our closed loop system, we obtain the transfer function of TS equaling KI plus KPS over MS squared plus B plus KPS plus KI. So using our closed loop transfer function, we need to set parameters for our KI and KP values. We did this by using the Ruth Hurwitz array, as you can see over there, and as a result, we needed to determine our stability gain limits, we need KI to be greater than 0 and KP to be greater than negative B. And using our settling time requirement of 8 seconds, we were able to obtain our initial values of KP equaling negative 7.55 and KI equaling 1. We are able to obtain zero steady state error due to our integrator, as you can see in our error function. We set that using the final value theorem. We were able to obtain zero steady state error. When we plugged in our initial values of K and KP into Simulink, we got a very oscillatory result, and it was still very slow. So we needed to go use the SISO tool, use the MATLAB to obtain our requirements. When we did, we ended up getting values of KP equaling 718.3 and KI equaling 3,559.3, which met our requirements of a settling time of less than 8 seconds, as you can see here, and it met our overshoot of less than 7%.
My name is Aaron Frank, and I'll be talking about the verification and robustness analysis of our system. After we achieved our control gains, we modeled our system in Simulink, including disturbances, with the gains that we found. And what we found is that our closed loop values had an overshoot of 6%, a settling time of 7.75 seconds, and 0 steady state error. All 3 of these are within the design criteria. Here we have the response of our system to 100 km/h input. As you can see, there's minimal overshoot, and we hit the desired settling time. Additionally, our system is BEVO stable. Up there you can see the root locus of our system. All gains of the poles are staying in the left half plane as gains go into infinity, so we will stay BEVO stable for all gains. Moving on to the robustness analysis, we've got our Bode plots for our closed loop system here. And based on the Bode plots, we calculated the gain and phase margin. We found the gain margin to be infinite, corresponding, our phase Bode plot never dips below 180 degrees, so the gain margin will be infinite. This means that we can add infinite gain and our system will stay stable, which means that even if there's gains we don't account for in our system will remain stable. Additionally, we found the phase margin to be 85.3. This can be used in this equation where omega is the crossover frequency of our Bode plots, and we use this to calculate the T max. The T max we calculated is 0.626 seconds, and that corresponds to the maximum amount of delay our system can handle and stay stable.
Now for conclusions. Driverless cars will make commuting safer and more enjoyable. By using a PI controller, the closed loop system can achieve the desired metrics. No steady state error, minimal overshoot, and a fast settling time. We would like to thank you for watching.